Hi everybody and welcome to a new exciting video in the audio signal processing for machine learning series. This time we'll continue our quest into the time domain audio features, and specifically we'll be extracting the RootMean squared energy and zero crossing rate features using librosa. Okay, so let's get started, but before that, I just wanted to tell you that we are going to be rehashing a lot of the code that I used in my previous video where I was extracting amplitude envelope. So yeah, let's just grab some of this code from here. Okay, so the first thing that I want to grab is just this imports here. So as you can see, I'm importing matplotlib, pyplot, numpy, librosa display for just displaying the waveforms, and then IPython display for playing audio directly in the Jupyter notebook. Okay, so the next thing that I want to do is just load some audio. And today, just like in the previous video, we're going to be using 3 audio files that are three music passages. One is by Debussy, an orchestral piece. Another one is a jazz piece by Duke Ellington, and the third one is a rock song from the Red Hot Chili Peppers. Okay, so let me just grab the path to these files, and then as a next thing, I just want to load them. And again, I'm just going to be reusing this code just to keep things quicker. Okay, so here the only thing that I want to change is I'm replacing that SR sampling rate with underscore, because we don't really need the sampling rate this time around, I believe. Okay, so now we should have the signals loaded for Debussy, Red Hot Chili Peppers, and Duke Ellington. As a first thing, we want to extract the RootMean squared energy using librosa. So let me write that down. So extract RMSE with librosa. So how do we do that? Well, we can use a simple function coming from librosa in the feature module. But before we do that, let's just create a couple of constants or variables. So the first one is frame length, and I'll put this equal to 1024 samples. So I'll use the same one that we used in the previous video, and same thing for hop length. And this should be equal to 512. Okay, so now let's extract the RMS for Debussy, and for doing this we'll do a librosa.feature.RMS, and we should pass in the signal for Debussy, and then we should pass a couple of parameters, the first one being the frame length, and we'll set this equal to our frame length variable, and then we have the hop length, and we'll set this equal to hop length. Once again, let me remind you that we can alternatively use both hop length and hop size, or frame length and frame size. We're referring to the very same concept. Okay, so now let me do the same thing for the Red Hot Chili Pepper song. So I'll do a RMS Red Hot, and I should pass in the signal for Red Hot in here. And here, let me pass the signal for Duke Ellington. Yeah, this was in the way, or the cursor. And here I should put in Duke. Okay, so let me run that. It seems like it works fine. So now, what do we get back from the RMS function? Well, you can guess it. We get a numpy array, but let's take a look at the shape of this numpy array. So we'll do an RMS Debussy dot shape. Okay, and so as you can see, we have a couple of dimensions. So the first one is just 1, and then we have 1292 values. Right, and so if you remember, and yeah, this might be a little bit hard to remember because it's just a number, but this is the very same number that we got when we extracted the amplitude envelope in the previous video, and that's because we were using the very same hop length, 512 samples, and we had the same duration for the audio signal. Now, what we want is this guy here. So in order to get just this, so what we can do here is just take the index. So we'll just like take this guy here at index 0. And now if we rerun this, this is just like equal to this, which is like what we wanted. Now, why did I want that? Well, because now we're gonna plot. So we want to plot the RMSE for all the music pieces. Okay. So now I'm not gonna rewrite the code like for like the plot, but I'm just gonna steal it from my previous video. So not here, I'm gonna steal the one down here. Okay. So let me go back here. And so let's do this. Okay. So let's see what we should change over here. So we have like our figure, we create a subplot, we create like 3 stacked, vertically stacked subplots, and we want to display the wave plots for Debussy, for Red Hot, and for Duke. And here we want to display not the amplitude envelope for Debussy, but rather the RMS for Debussy. Here we want to visualize the RMS for Red Hot Chili Peppers, and down here for Duke Ellington. So now there's one thing missing. So it's just like this T value, and again I'm gonna just grab it over here. So basically, like, this is the X, the value for all the values like on the x-axis that you have like down here, and here this the RMS Red Hot, for example, is the values for the y-axis for our plots. And obviously what we want to do is just like move from frames like to time, and we can do this like using the frames to time function that I introduced in my previous video. Okay, so now this should do the trick, unless I messed up something like in the code. So let's see if it works. And indeed, I messed up something. And that's, oh yeah, right. That's because I was passing the amplitude envelope for Debussy, but we don't have that. We had that in the previous video. So let me just grab RMS for Debussy. Now, the length for RMS Debussy, RMS Red Hot, and RMS Duke is going to be the same, because we have these files that have the very same duration, 30 seconds. Okay, so now let's rerun this, and it's here. We have it. So in red, you can see the RMS energy, in this case for Debussy, here for the Red Hot Chili Peppers, and here for Duke Ellington. Okay, so as you can see, we still have like ideas that are like more or less like comparable to what like we discovered in the previous video with the amplitude envelope. But the cool thing here is that we have like way less like variability and outliers, and that's because for the RMS we are considering all the samples in a frame. We're not just like taking the max value of the amplitude for a given sample inside like a frame, right? And now, just like for the sake of comparison, let's just compare the amplitude envelope. So this is the amplitude envelope for Debussy, for Red Hot Chili Peppers, and Duke Ellington, as we extracted like last time, and compare that against this, the RMS. And as you can see, as I was mentioning, so here, like this just like it goes crazy, right? We have like a lot of spikes, and it just like follows like the upper part of the envelope, obviously. But here, everything like is toned down. And again, this is like because we are considering aggregating the results for all the samples in a frame. Okay, but Okay, so here, now you know how you can extract the RMS energy with librosa, but wouldn't it be nice if we try to extract the RMS energy from scratch? Yes, it will be nice, so let's do that. Okay, so let's create a function that we'll call RMS. So what does this function get as an input? It gets the signal. It also gets the frame length and it gets the hop length. Again, this function is going to be like quite similar to the function that we built last time for the amplitude envelope. So, but before we get in here, so what I want to do is just like show you the RMS. Okay, let me show you that. So this is like the formula that we use for getting the root mean square energy. And so we do like we take the RMS of all the samples like in a frame. And so here you have like the RMS calculated at frame t, and as you can see, what we should do here is basically just calculating the energy first. Then we should like sum the energy of all the samples in a frame, and then once we've done that, we want to divide by the number of samples that we have in a frame, or the frame size, and then we just take the square root out of that. So we should convert this into code. Let's do that. Okay, so the first thing that we want to do is just create an empty list, and this is going to contain the RMS for each frame. Okay. And now we want to just loop through all the frames in the audio signal. And so for doing that, we can say for I in range, and here we start from 0. We should stop at the length of the signal, and the step that we should use is the hop length, right? So at every step, we are moving the number of samples in the hop length like to the right to start like a new frame. Now, if you want to get like the details about this, I suggest you just like go check out my previous video on the amplitude envelope where I explained this like in detail. Okay. Now, what we should do here is basically calculating the RMS for the current frame, and the RMS for the current frame is given by this formula here. So yeah, let's try like to put this like in place. So what should we do here? Well, first of all, let's take the NumPy sum, and we should take the sum of the signal. And out of the signal, we want to slice only the samples in the current frame. And for doing that, we should like slice it between I and I plus frame length. And I've just discovered I have a typo, so let me correct that. Okay, frame length over here, which is cool. And okay, so once we've done this, we should square this value. So basically, I'm just doing this. I'm taking this guy here, and I'm taking like the sum of all of this, of the energy. And once we've done that, the next step that we want to do is divide by the frame length. And finally, we should do a NumPy.square root. Okay, so this should work. And out of like all of this guy, we should get the RMS for the current frame. And we want to append this to the RMS list. So we'll do an RMS dot append, and we'll pass in the RMS current frame. Great! So now we can return RMS, but before doing that, we'll convert this bad boy to be a NumPy array. So, done this. Okay, so this should work. So now let's see if it actually works. So we'll do let me just like grab this. Use this guy down here or here. So let's say RMS1 red hot and RMS1 Duke. So now obviously we're not using the librosa implementation of RMS, but our own, the homemade, the sound of AI RMS implementation. And I think like the arguments are the same. The only thing is we don't want to take like the element 0 here. And yeah, this seems to work. But now let's see if this actually works by comparing like our implementation to the librosa one. So how do we do that? Well, we just like get this guy here and we'll just like replot everything, but adding our implementation as well. So we'll do a plot and we'll pass in T, then RMS1 Debussy, but we want to change the color, and yeah, let's put it to yellow, for example, here. Yeah, we'll do the same thing with the red hot piece. And then we'll do the same thing for Duke Ellington. Okay, so now let's plot this. And obviously I have an issue here. And yeah, yeah, this typos. So I was just missing this equal sign over here. Okay, let's go and see. Yeah, and as you can see, basically like you can't kind of like see the red halo, like just like below the yellow like RMS, like our RMS. So basically this means that the two implementations like gave us the very same result, which is nice, and it seems like that like our implementation is working. Great. Okay, so now we want to move on to another thing, which is the ZeroCrossing Rate. Okay, so how do we extract the ZeroCrossing Rate? Well, again, this is really a piece of cake because of librosa. So now I'm just gonna grab this, and instead of having like RMS, we'll say ZRC, so ZRC. So this is the, or well, I should say ZCR, so ZeroCrossing Rate. Okay, so we're getting the ZeroCrossing Rate. Obviously what we should change here is we don't want to take the RMS from the feature module, but rather the ZeroCrossing Rate. Okay, so let me replace this here. And then the arguments are the very same arguments. Okay, so now we can take this. Okay, so now what I want to do is just plot these guys. So let's visualize the ZeroCrossing Rate for all the music pieces. Okay. So how do we do that? Well, we can always use like the same kind of like template that we've been using so far. Well, yeah, but perhaps yeah, I want to change it like this time. So yeah, so what I want to do here is only have a single like a figure, so no subplots, and then have all the different, the graphs for the different like zero crossing rates for like the different pieces inside the same thing so that we can compare it. Okay, so let me do that. So I'll do a plots.plot t. Here it's not RMS Debussy, it's ZCR Debussy. So we want this. Then I'll just copy this down here and I'll say ZCR, and here we want the Red Hot, and here ZCR for Duke Ellington. Okay, so now I know, because I already tried it, that we can, so we are going to get basically like the values for the zero crossing rate are going to be normalized by the number of samples that we have in a frame. So they're normalized by the frame size so that we can get as a maximum a value of 1, which would be like changing like sign at every value. Okay, but because of that, I'll put the range on the y-axis between 0 and 1. Okay, so I don't want a title here. I just want to do a plot show down here. So let's see if this works. Here we go. Yes, but there's a problem, right? So now all of them are in red. So now we could put the WC one in yellow, Red Hot Chili Peppers. You guess what color I'm going to use that. I'm just going to keep red there, here. And here for Duke Ellington, I'm going to put blue. Okay, so let's see. And here you have it. So, as we said, in yellow we have Debussy, the zero crossing rate for Debussy. In blue we have the one for Duke Ellington, and in red the one for the Red Hot Chili Peppers. Now, is it a surprise that the Red Hot Chili Peppers have kind of like the highest zero crossing rate? No, and that's because like they are using a lot of like percussive instruments, and usually rock music has a ZCR that's kind of like higher than classical music. And here indeed you have like for the Debussy zero crossing rate over time, that's like quite low. It goes up probably when we have like the climax in the music, and perhaps because we are getting also like higher like with pitch, and that determines a higher like zero crossing rate. And the blue zero crossing rate for Duke Ellington is a little bit like all over the place, and it seems to be a little bit like in between the one from the for the classical music and for the rock music. Now, if you want the actual values of the zero crossing rate and not just the normalized ones, so what you could do is take this guy and multiply it by the frame length. Okay, so we are gonna multiply the vector by the frame length, and now if I remember correctly, like we could put like between 0 and 300 the range, and it should be fine like this. Yes, yeah, let me just put a little bit more. Oops. Over here, let's try 500. Yes, looks good. Okay, so, and this is the actual number of zero crossing rates, the absolute number of zero crossings that you have like in these different signals. Okay, so now I'm not done yet, because another thing that I want to try is to see the zero crossing rate on some voice and compare that against an audio signal that only has white noise. Okay, so let's try that. So for trying that, we should just like load a couple of things, and so we'll do a voice file, and this, if I remember correctly, I should have stored it in audio inside the current like folder for like video 9, and it's called voice.wav. Okay, and then we have the noise file, and this is called, oh, sorry, it's in the audio folder, and then it's noise.wav. Okay, so now let's try to actually load these guys first. So I'll do a voice and then for underscore, and we'll use again librosa.load, and I'll pass in the voice file. And here I'm going to be using another really cool feature or argument that you can pass to librosa load, which is the duration. So you can't, by passing like this argument, you actually tell librosa how much in terms of seconds you want of the audio file. Okay, so we'll say 15 seconds. Okay, and I'll do the same for a noise. And here it's not the voice file, but it's the noise file. Next thing, we want to listen to these audio files directly in the Jupyter Notebook. So for doing that, we can easily use ipd.audio, and then we'll pass in the voice file. Here we go. And here we have like our nice little player, and I'll pass in the noise file over here. Okay. It should go. Okay, so let's listen to the first 15 seconds of the voice chat.
Jack Pepsi CD.
I was just checking out.
What do you think about that, Clint?
I like the little Tad Pepsi logo with
it's
on
like
the front.
It's like a Pepsi logo, but it says Tad instead of Pepsi.
Yeah.
It's pretty.
Yeah, so you get it, a highly philosophical discussion about Pepsi logos. And here we have some white noise. Delightful, isn't it? Okay, let's get the ZeroCrossing Rate for this too. So we'll do a ZCR voice, and once again we'll do a librosa dot feature dot ZeroCrossing Rate, and here we pass in the signal, so it's voice, and then the frame length, and I'll pass the hour frame length and the hop length, and let me pass the hop length over here. And now I'll just copy paste this because I'm too lazy to rewrite that. So ZCR noise, and here we want to pass noise. Okay, looks good. Now let's grab this guy over here, just to visualize the voice and the noise in the same graph. Okay, so let me just copy ZCR voice and paste it here, and then do the same thing for noise. And now we'll just like keep the normalized version of this. So I'm just gonna get rid of these guys, and this should be in range 0, 1. So now let me just like put this like to 12, because before like it was like too high, wasn't it? Okay, yeah, we have an issue here. Yes, that's a good one, right? So like the mistake here is basically I passed like this t, right? But this t was calculated on the number of frames that we had for the previous, for the music passages, and that was like 30 seconds worth of audio. Here we only have like 15 seconds worth of audio, so we'll have to recalculate this t value. Okay, so for doing that, we'll do iframes, and here we should do a range between 0 and the length of ZCR voice. Okay, and then the next thing that we need to do is just like get this value here, and for that we should use, where is it? Over here. Yes, here it goes. This function from librosa. Okay, so frames to time, and we should pass in frames. Now there's another mistake that I noticed. So here we should take the value at index 0. Okay, so now let me redo this, and hopefully this time it should work. And indeed it does. Okay, so in a yellow you should have the voice, and in red the noise. And as expected, usually the white noise has a number of crossing rates that's higher than voice, and that's it. Okay, so you now get the idea of how to extract zero crossing rate using librosa, and we've also seen how zero crossing rate changes in different music styles, as well when we compare it for voice and noise audio files. So yeah, that's it. So we are basically done with the temporal audio features. So next time we'll start looking into frequency domain features, and specifically we are going to be starting looking into the Fourier transform, which is going to be our very important tool that we'll need for getting any information in the frequency domain. Okay, so I hope you've really enjoyed this video. If that's the case, please give it a thumb up. Then if you have any questions, as usual, just post them in the comment section below. One thing that I want to remind you of is the Sound of AI Slack community, which is a community where you'll find very interesting people who are interested in all things AI audio, AI music, digital signal processing. So if you want to grow your skills, grow your network as well, I suggest you to go and join this community. I'll leave you the link to the community in the description section. Okay, it's all for today. I hope I'll see you next time. Cheers.